Also, thank you for the keynote speaker, which is Professor Gaffo. Very interesting spacer modification and design and close to commercialization. And today, my topic is using nanomaterials to combat the fouling of the membranes. So the topic I will talk is using two-dimensional molybdenum disulfide nanoplatelets as fouling-resistant membrane surface. So, yeah. So we know rivers, lakes, dams, and groundwaters, they are the conventional water resources. They are the best way to get fresh water supply. However, in many parts of the world, particularly in the dry climate zone, like in UAE, so such conventional water resources are not readily available. Then we need to turn into non-conventional water resources, such as seawater. Because of the salt present in the seawater, so we have to employ technology, which is desalination, to separate salt from water. And also treated wastewater is another good resource of a non-conventional water supply. But we need to further treat it to remove the low level of micropollutants in order to reuse and recycle. Another emerging new non-conventional water resource is atmospheric water vapor. Through using technologies such as cloud seeding or fog catching, we can capture and harvest this important non-conventional water supply. So talk about the desalination. So based on membrane technology, the membrane fouling is still the most major operational challenges. So how it happens? So when the water molecules pass through the membrane, they left behind all the impurities or contaminants. So this either dissolved solids or suspended solids will be washed away by the cross flow and end up in the reject. However, along with the time, a small portion of these dissolved solids will become attached on the membrane surface or inside the pores of the membranes, and fouling of the membrane occurs. We know the occurrence of the fouling of the membranes will result in lower than better than planned water production, and the salt rejection may be affected as well. And even worse is the further progress to biofouling. So the bacteria, the odd one or two bacteria become attached onto the membrane surface, on the conditioned membrane surface, and then they will discharge this very sticky extracellular polymeric substance called EPS, and then to help them attached further firmly with the membrane surface for their colonization and grow in the numbers exponentially. You probably will say disinfection, for example, by chlorination of the feed solution can solve the membrane fouling. That's only part of the solution. So indeed, we also need to work from the membrane side. So for example, we need to develop fouling resistant membrane surfaces, which make the attachment, particularly the initial attachment of those organic matters much harder in order to delay the onset of the membrane fouling. So molybdenum disulfide, MOS2, is a transitional metal like chalcogenide called TMD layered compound. So 2D layered compound means it has a morphology similar to graphene nanosheets. However, it has a different crystallite structure. So as shown in this image, it has a tri-layered sulfur, molybdenum, and sulfur, three-layer crystallite structure. Industry-wise, before nanotechnology come along, so the MOS2 powders is used as an anti-friction material, so-called solid lubricant. So in this research, we synthesized molybdenum disulfide nanoplatelets first, and then coated them on the nanofiltration, commercial nanofiltration TFC membrane surface with the help of bridging material L-DOPA and study its antifouling resistant property. So the synthesis of this nano material molybdenum MOS2 started by using sodium molybdate salt with the green sulfur source L16, undergo this hydrothermal reaction at a very low pH. So we obtain this blackish nanomaterial. Observation under the scanning electron microscope, so we can see this stacked nanoplatelets morphology. Further, so they are stacked, but by ultrasonication, we can separate them before coating. So the TM image also can be reviewed. It is a nanoplatelets. You can see the transparent nature, so they are not 3D. So their presence of molybdenum, sulfur, both confirmed, and XRD shows a very weak representative peaks, probably due to the 2D structure. So this photo and SEM image shows the neat membrane and in comparison of the coated, surface coated membranes with the MOS2 nanoplatelets. So firstly, we analyzed the interactive adhesion force by using atomic force microscope. So if you look at the left graph, so the force in the negative range means promote adhesion. So the force in the positive range promotes repulsion. So if you look at the blue curve, that represents the coated membrane surface. They have a very weak solvent adhesion force. So not positive or negative. However, the neat and coated one has a slightly negative force. That means they are more likely to be attached. So the right side is a zeta potential, streaming zeta potential. So the coated membrane surface is negatively charged in the normal pH, like 7. So these 2D MOS2 nanoplatelets possess naturally dispersive surface tension, which contributes to positive free energy exchange, which is in favor of anti-fouling or fouling resistant. So this is the underneath mechanism of this material. So membrane filtration was carried out to evaluate the flux and fouling behavior of the coated and compare with the neat membranes. If we look at the top graph, you can see it shows the filtration of 1 hour. At the end of 1 hour, you can see the coated membrane almost didn't show any significant decline of the relative flux. However, the L-DOPA coated, it's continuous decline. Hold up a little bit at the very beginning, continuous decline. So the bottom graph shows at the end of 10-hour fouling experiments, cross-flow setup. So we can see the MOS2 coated has much less flux reduction compared to the neat membrane, which has much severe flux reduction. So that suggests MOS2 has quite effective anti-fouling property. So the MOS2 coating does not significantly affect the salt rejection of these commercial TFC membranes. So you can see slightly increased salt rejection. Both neat and fouled membranes uncoated and coated membrane were thoroughly washed by water for 1 hour. So we found the recovery of the flux of the neat membranes is 68%. However, much higher recovery was found for the coated one, which is 85%. So this suggests the coated surface detachment of the foulant is much loose and easy to be removed. In addition, we conducted some comparison of 2 different nanomaterials. which is this MOS2, and with another one, which is GO. They both sheet materials. So this is a GO. We use the dispersion, the nanosheets dispersed in the solution. And this is the MOS2 dispersion. So this time we're using a porous membrane. They were deep coated. So as illustrated here, this is not TFC. They can go into the porosities of the membranes. If we look at the results of this comparison, so within the first hour of cross-flow filtration experiments, by the way, the BSA 1 grams per liter is used as an organic solvent in this accelerated fouling experiments. So you can see within first hour, the coated MOS2 coated membrane has less fouling reduction. However, the GO and the non-coated both experiencing flux reduction. So the lower graph shows 10-hour filtration results. So at the end of the 10-hour filtration, which represented longer-term filtration experiments, we can see uncoated, which is a green one, shows 40% of flux reduction, which is the worst fouling happening. And GO coated shows 25% of fouling reduction, flux reduction, and MOS2 coated has 20%. So compare between GO and MOS2 coated, probably due to the MOS2 coated surface is more hydrophilic than GO, because we measured its contact angle. They found the MOS2 coated has the lowest water contact angle. In the biofouling experiments, so we collected the fouling layers scraped off from 3 fouled membranes, uncoated, MOS2 coated, and GO coated. So then the bacterial population were analyzed or counted by the instrument flow cytometer. If we see this graph as the bacterial population of the uncoated membrane is 100%, then we found the MOS2 coated one has 67% less bacterial counts than uncoated, and the GO coated has 39% less bacterial counts than uncoated. So both pointing to they have some effects of fouling reduction, particularly in the biofouling situation. We use the natural unchlorinated water for the biofouling experiments, and among them, MOS2 shows better effects. So for my short presentation summary, so the TFC NF membranes coated with MOS2 nanoplatelets demonstrated significant fouling resistance effects. Such anti-fouling effects were underpinned by combined unique interfacial factors and properties offered by 2D molybdenum disulfide morphology, include dispersive surface energy tension, reduced surface roughness, weaker MOS2 foulant interactive forces, and negatively charged membrane surfaces. Okay, acknowledgement of my postgraduate students, and thank you.
Thank you very much, Dr. Su, for your very nice presentation. We have time for one question, and I have here one question. It's about interactive adhesion forces were measured with AFM. Can you give us some additional details how you did this?
Oh, so that is mostly by theoretical literature review. Okay, so there are literature's report about the calculations of interactive forces, particularly for molybdenum disulfide. At this stage, I only study the equations and apply those relevant equation parameters to our situations.
And maybe one last question, a very short one. What is the thickness of the coated layer?
Oh, the thickness coated layer because of the roughness of the membrane, it's very hard to measure. Okay, depends on the time. The longer time we coating, the more. But the idea is we just arbitrarily decide coating 24 hours. That's it. Yeah. So I really, at this stage, just qualitatively evaluate its time effects. Yeah. So very thin, because if it's thick, they will not able to stay attached properly. But if it's thin, so due to the nano size, nanostructure, the van der Waals force will be able to help to keep the coated material stay in place for longer time. So that's the difference of nanotechnology and normal technology. It has to be thin.
Yes. Yeah, then thank you very much for your presentation. Very nice. And also thank you for your answers.
Thank you.
All right. So I think now our president, who was introducing the two first speakers, is the next speaker. So I introduce Professor Frank Lipnitsky to start his presentation on, of course, we are in the fouling session, so fouling investigation on fouling and scaling and cleaning of membranes, and this time maybe specifically for wastewater municipal wastewater treatment. Professor Frank, floor is yours.
Thank you very much. I hope you can see my presentation. So I talk about investigations on fouling and cleaning for direct membrane filtration.
Can you share your presentation?
Oh, is there something went wrong? Sorry, I thought I... Oops, window. No, it's...
Yeah. Okay.
Yes, now it should.
No. All right.
Okay. So I'm talking about investigation on fouling and cleaning for direct membrane filtration of municipal wastewater. So we move away from the desalination to wastewater. And I would like also to acknowledge my co-authors, Simon Giestedt, Omar Khalid, and Gregor Rudolph. So first of all, some of you might not be familiar with direct membrane filtration. It's basically a wastewater treatment process where we try to avoid actually biological treatment. And so what we do is actually we take the raw sewage water, screen it into a feed tank where we remove the sludge for discharge, and then we use microfiltration, ultrafiltration to get out a nice permeate. And then the concept base is based on the fact that basically the COD fraction consists partly of particular organic matters which can be easily separated by microfiltration and ultrafiltration. And what we want to do with the retentate and also the sludge, we want to use it for biogas production. So we want to produce energy. And one thing we looked also at is actually the permeate after the ultrafiltration, microfiltration. Here we want actually to upgrade this permeate with activated carbon and ore forward osmosis. Just briefly, how does it work? When you look really on the particle size distribution of municipal wastewater, you can see you have particles greater than 100 microns, you have particles greater than 0.2 micron, you have soluble compounds, and certainly a lot of water. And when we look at the different types of processes, what we can see is actually when we use particles, we can, with a microsieve, we can remove particles greater than 100 micron. When we use basically microfiltration, we can remove particles greater than 0.2. So the only thing which we have remaining in the permeate are soluble compounds and certainly water. We tested this concept on 2 pilots before we moved ahead to the next challenge. And actually one of the next challenges we looked at was actually the increase of use of pharmaceutical and other types of organic compounds with different types of biological effects, which are entering our water system. And basically, most wastewater treatment plants are not designed to handle these compounds. So basically what's happened quite often, the compounds, pharmaceuticals go into the wastewater treatment plant and they come out at the outlet of the wastewater treatment plant. And these pharmaceuticals and micropollutants can have certainly a negative impact on the ecosystem. So the fishes don't like necessarily what we use as pharmaceuticals. And also the question is, what is then happening with our drinking water? Because, I mean, these pharmaceuticals are entering our water cycle. So they go with the water into the ground. We take out the drinking water from the ground, and yeah, how this has happened. So the best thing would be to find a nice way to remove them before. What we are coming up with is a concept which actually combines direct membrane filtration with coagulation and flocculation as initial step before the microsieving. And then we tested two different types of membrane processes, microfiltration and ultrafiltration, followed then by granulated activated carbon to find out whether this could be a way to at least reduce or even eliminate pharmaceuticals in the outgoing permeate or water from this concept. Just to give you an impression of the pilot plant we used. So the first step in our pilot plant was actually coagulation flocculation. And here we had a wastewater flow of 3 cubic meters per hour. We used a coagulant, which we dosed into the tank, and we used an anionic polymer as a flocculant. Then after this coagulation step, we had our microsieve. And it was quite a nice microsieve with a drum filter with 100 micron screen. We had an intermediate tank also installed with 600 liters. And from the microsieve, we then went further on to microfiltration and ultrafiltration. Here we used actually basically, you could say, an MBR type of concept. Basically, we used flat sheet membranes, plate submerged directly into the feed tank. The interesting thing we did is actually we used two different types of membranes. We used a microfiltration membrane, in this case an 0.2 micron membrane from Alfa Laval, and also an ultrafiltration membrane with an 0.01 micron pore size, which is equivalent about to 10 kilodalton in molecular weight cutoff. And that was the UFX membrane we used there. It's a hydrophilized polysulfur membrane. So with these two membranes, we did our direct membrane filtration. And after the direct membrane filtration, we had our granulated activated carbon set up. And we had 3 columns with granulated activated carbon, because in column number 1, we wanted actually to treat the standard wastewater treatment effluent. Then we wanted to have the treat the microfiltration permeate and the ultrafiltration permeate. And the empty bed time was 10 minutes. Contact time was 10 minutes. So some results. We were very happy to see that we achieved actually a quite good reduction of COD, TOC, total phosphor, and total nitrogen after microsieves, but even a further improved after microsieving and ultrafiltration. So what you can see is here, we achieved a very good, close to around 90% reduction of COD. TOC was reduced close to 90% also, total phosphor close to 100%, and nitrogen, we had just a removal of about 35%. So in total, the concept is working very well. But one of the other things we certainly wanted to analyze was actually, how does this concept actually do it with the pharmaceuticals? And this shows actually 26 different types of pharmaceutical compounds, which we selected to analyze. And basically what we saw is actually for 97% of the 70% removal of these components after the granulated filtration. So we can see actually that this granulated activated carbon as a final polishing step is a very, very interesting step forward to remove pharmaceuticals from wastewater treatment plant effluents. However, we're talking here about membranes, and one thing certainly we also look is actually how did our membranes perform. And what we try to do is actually we looked at the fluxes, and we try to keep the fluxes relatively stable at just 15 liters per square meters per hour. And what you can see here, that we achieved this quite nicely. That you see drops, and that was one of the mechanisms we reduced to reduce fouling. It was actually relaxation, so we basically stopped the membrane process for some time to actually relax the membranes and therefore reduce the fouling on top of the membranes. And that you see also that this was quite an efficient way to do it was actually, you can see in this, on the fact that actually after each relaxation, the membrane flux went up again. But basically we
Hello? I am the only one not hearing. We lost him.
Hello, Frank.
sorry.
Yeah, he's back.
Okay. Somehow our feeling was that actually this clinic was not so efficient. So what we did there is actually went to lab trials, and what we try to do is actually simulate actually the large scale process on a smaller scale using this small scale lab unit M10 from Alfa Laval. So this is basically the lab scale process where you have where we have basically the same setup. And what we found out there is actually we tested different cleaning protocols. So we tested different cleaning agents, and we did also two different types of concept. One was called cleaning in line, where we were flushing with a cross velocity of 1 meter per second without any permeation. And we did also soaking. And what we found out was
Frank,
actually, yes.
Frank, how many slides do you still have? Because we lost the sharing. We lost the sharing.
Wait.
Sometimes, yeah. I mean, yeah. So try to make it, yeah. Because
I try to share.
Share again, yeah. And please, yeah, try to make it fast.
Yes, I'm as fast as possible. It's not so long more. But basically, what we saw is actually that the caustic cleaning was the most superior cleaning compared to the citric cleaning, and also we found out that actually when we recirculate the cleaning liquid, it was more cleaning efficient than actually just the soaking. So after 1 hour of recirculation, we had a similar effect, close to a similar effect than actually 4 days of soaking. So what were the learnings we got? Was basically we found out that when we reduce permeation and increase the relaxation frequency, we get a better performance. Cleaning in line, that means with flushing, was better. Cleaning chemicals, we found out that the caustic cleaning agent, in this case Ultrasil 10 from Ecolab, was more efficient than other cleaning agents. And last but not least, one should do the cleaning at the highest temperature possible. And certainly that's their limitation when you do it in a wastewater treatment plant. So in conclusion, what I wanted to show to you was basically we developed this, or we're working on developing and improving this concept of direct membrane filtration, where we have a pre-treatment with flocculation, coagulation, a microsieving, and then we have either microfiltration or ultrafiltration as a step to actually polish the wastewater further, with the aim that we can actually recover resources for biogas or production or as fertilizer, and to have basically after activated carbon a very nice permeate which we can send then out to the nature. And one of the things we certainly find out, cleaning a place with Ultrasil 10 can almost completely restore the permeability of the membrane, and is therefore a nice cleaning method. And last but not least, I would like to thank then also our sponsors for this project, the European Union, the Less is More project, Sweden Water Research. And we had also, OMAT was part of the Erasmus Plus program on membrane engineering. Thank you very much. And sorry for the technical problems.
Thank you so much, Professor Frank. This is the real life presentation with a big system, so completely different than very small scale. I do have one question from Professor Yassin. So sieving is at the edge of technology. How could sieving becomes further efficient?
That's an interesting question, because I mean, we could look, for example, to use different types of sieving configuration. So basically look at the holes of the sieves and look if we can do improvements there, and also go maybe as we selected now a 100 micron sieve in this case, but maybe we should also test different sieving mechanisms as a pre-treatment. But we saw actually looking on the particle size distribution we have actually in wastewater, the 100 micro sieve was actually quite a good selection.
So Professor Frank, is your UF or MF dead end or cross flow?
It's dead end with yeah. It's basically it's a membrane bioreactor design, you could say, without biology.
Okay. So please join me in thanking Professor Frank for this very good presentation with the very large-scale commercial demonstration. Thank you very much, Professor Frank.
Thank you.
Okay, so let's go with our last, but for sure not least, presentation of this session by Professor Lee from Songholi team, which are very active in membrane distillation and other technologies. But so today, Professor Lee will give a presentation on the effect of vibration types on membrane fouling in DCMD. The floor is yours. Thank you.
Okay, thank you for introducing me. And my name is Ju-Young Lee, and I'm in the doctoral course at Kookmin University in Korea. My topic today is the effect of vibration types on membrane fouling in direct contact membrane distillation.
Can you please share the screen?
Oh, sorry.
Yes, we see.
This presentation will be delivered with the following contents. And let me talk about our motivation of research briefly. As you know, the global water shortage is becoming more and more severe, and one of the promising solutions is seawater desalination. However, conventional technologies such as MSF or RO require a large amount of thermal or electrical energy. Accordingly, emerging technologies such as forward osmosis and membrane distillation have drawn attention as alternatives to the current desalination technologies. Membrane distillation is a thermally driven process that uses a hydrophobic membrane as an evaporator. It has several advantages of being able to operate at relatively low temperatures and pressures, theoretically 100% removable for non-volatile solute, and be able to handle to very high concentrations. When MD is applied, there are 4 different ways of implementing MD as shown in the figure. Among them, we choose direct contact membrane distillation, which has the simplest configuration with capability of easy operation. One of the most serious problems in membrane processes, including MD, is scaling. Once scales are generated, they are difficult to remove because the bonding force between the crystals and the membrane increases after a certain time period and consequently makes the OPEX higher. According to a research among a lot of scaling ingredients, calcium sulfate was found that accounted for the largest portion with 42%. Among various methods, our study focuses on the scaling control by vibration of membrane modules. We first examined the effect of vibration on scale control in DCMD. Then we also compared the effectiveness of different vibration patterns, including regular vibration, random vibration, and vibration created by music signal. In addition, we explored the correlation between RMS energy consumption to anti-scaling effect. And here comes the experiment setup and conditions. You can see our experimental setup on this slide. This is a typical DCMD system consists of hollow fiber membrane with vibration generator. The whole hollow fiber module was vibrated to mitigate the scaling during the operation. We used Equinity commercial hydrophobic hollow fiber membrane made of polyethylene with 65 square centimeter of effective membrane area. All chemicals were purchased at Sigma-Aldrich and mixed with high purity deionized water. According to the flow rate we set it and the area of module and membrane, liquid flow type of both feed and permit was laminar flow condition. Temperature of both solutions were carefully maintained and monitored. Now on, I'll explain the result and discussion. This slide shows the changes in flux with VCF during the DCMD operation. This is the control experiment, so there was no vibration applied to the membrane module. As expected, the flux was reduced due to scale formation. The flux gradually decreased with the time and then rapidly dropped after the VCF of 2.7. This may be attributed to the formation of calcium sulfate crystals after a certain induction period. The mechanisms are schematically shown in this picture. And to mitigate flux decline due to scale formation, we first applied the regular vibration to the DCMD module. The vibration frequencies were 100 and 200 Hz, respectively. The results are shown in this figure. It is evident that the regular vibration can retard the flux decline. The initial flux of 200 Hz were higher and flux declines were also less serious than 100 Hz. As the vibration frequency increases from 100 to 200 Hz, the flux increased and the blocking coefficient was reduced. However, the difference between the two frequencies was not that much significant. To quantify the vibration efficiency, the vibration value was measured using two vibration sensors. One sensor was attached to the vibrator and the other one was attached to the module. The ratio of these measurement results indicates the transmission efficiency. When the frequency changes from 0 to 240 Hz, the vibration value of the vibrator ranges from 0 to 2.7 GRMS. On the other hand, the vibration value of the module was different from that of the vibrator, which ranges from 0 to 1.0 GRMS. When the frequency is higher than 200 Hz, the difference in the vibration value between the vibrator and the module increases, suggesting that the vibration energy is not efficiently transferred from the vibrator to the module. This can be also confirmed from the transmission efficiency in this figure. At 100 Hz, the vibration transmission efficiency reaches the maximum and the vibration transmission efficiency decreases significantly at the frequency value of 200 Hz or. Based on the previous results, we found that the vibration frequency is an important factor. In the regular vibration, the vibration frequency is fixed at a constant value. Here, we try to vary the frequency by applying certain signal inputs. We considered two additional vibration modes depending on the types of the signal input. The first one is the random vibration, which is created by a random signal input. The second one is the patterned vibration, which is created by a music signal input. In this slide, the random vibration was applied to DCMD. As shown in figure, the vibration using random frequency in the previous range of 850 to 7,650 and 650 Hz had little effect on the membrane scaling. The rapid flux decrease was observed at almost same point with the result, which was conducted without vibration. Furthermore, the ending point where the blockage coefficient becomes 1.0 of both experiments were 2.85 and 3.0 0.05 of precip, respectively. Since the random signal input was not effective, we tried to find a different signal input for the vibration. Here we selected a music file as the signal input. The left figure shows the frequency distribution of the music signal used for patterned vibration. The right figure shows the vibration value of the patterned vibration, which was measured in the experimental setup. We set the vibration value of the patterned vibration to 1.7 G RMS. When the patterned vibration was applied, a significant increase in the flux was observed as shown in this figure. This implies that the patterned vibration is effective to mitigate flux decline due to scale formation. It should be noted that there was no anti-scaling effect when random vibration was applied. This suggests that there should be appropriate vibration patterns that can effectively control fouling due to scale formation. Here we compared the results of regular vibration with those of patterned vibration. In both cases, the vibration values were set to be the same, which as 1.7 G RMS. Although the regulation vibration at 100 Hz were effective to retard flux decline, the patterned vibration was more efficient. To further investigate the effectiveness of the vibration, the energy consumption for the vibration generated by different signal inputs was measured using a digital power meter. When the regular vibration was applied, the energy consumption was 53 watts. With the random vibration, the energy consumption was 56 watts, which is higher than that of the regular vibration. With the patterned vibration using the music signal, the energy consumption was 47 watts, which is lower than that of the regular vibration. It should be noted that the patterned vibration was more effective to mitigate scale formation than the regular vibration, even with a lower energy consumption. These are our conclusion of the study. We first examined the effect of regular and random vibration on scale formation in DCMD. The regular vibration was effective to mitigate scale formation. However, the effectiveness of the vibration was not proportional to the vibration frequency. The random vibration with the range between 850 and 7,650 Hz did not retard flux decline due to scale formation. We also investigated the effect of patterned vibration. The pattern vibration was more effective in alleviating the scale formation than the other vibrations. The energy consumption of the vibration generation using specific patterns frequency was relatively lower than that of the specific continuous frequency under the condition of similar fouling control. There seems to be a possibility of further optimization of the vibration patterns for higher anti-scaling effect and lower energy consumption. And thank you for listening to my presentation.
Thank you very much, Dr. Lee, for this very clear presentation. I do have one question in the chat, but I also have one question. So I will start with the chat. What is the amplitude of the vibration?
The amplitude we used was 1 milliV peak to peak. It was 1 milliV voltage peak to peak was the amplitude we used.
All right. So, my question is regarding the vibration system itself, because it just maybe I didn't capture the system. How much this is different than ultrasound? Because you are using with the same stuff, but you said it's a mechanical vibration, but I didn't get how this is it. How much different than ultrasound, which is also used? It was used for MD and others.
You mean the ultrasound versus this vibration? right?
Or just focus on yours. Well, I mean, how you said it's mechanical, then you gave a different amplitude and different frequency.
So the sound is not.
Okay, there's another question. It seems that the vibration has very limited effect on the membrane distillation. Can vibration explored further in the MD?
Yeah,
Another question.
Yeah, we vibrated the module of the hollow fiber module. We vibrated the module in this study, but we also considering about vibrating the membrane, not the module. So it will, I think it could be more effective than the vibrating the module. So we are going to research about the vibration, applying vibration to membrane directly. So yeah.
All right, so it's very clear. So as I said, we had just a few publications on ultrasound for MD, and other people are using different kinds of vibration. Maybe it's good to compare with your system in the future.
Yeah, that's right.
When you have your publications.
Yeah,
So with this, myself and Professor Frank would like to thank you very much for attending this session to the end. Unless Professor Frank will conclude something before this, we close the session.
No, we can close the session. Thank you very much to all the participants for their excellent presentations. And it was really a pleasure to be part of this conference. See you soon, hopefully physically.
All right, so I thank again all the speakers, and unfortunately we cannot see the participants, but we see that there were like 32 participants. Thank you very much, and we give you some time for catching up with the break and then the next session. Thank you very much for your attention. With this, we close the session.
Thank you. Bye-bye.